Hey, Katie.
Hi, Ben.
I'm going to read some lyrics. I want to see if you know them.
Okay.
It's astounding. Time is fleeting. Madness takes its toll. So
Oh,
you know what
yes.
I'm saying.
Yeah. Are we gonna do the time warp again?
Let's do it. You are listening to Linear Digressions.
Oh, I love that song.
Yeah, and the again part too.
Oh, yeah. Okay. So what are we talking about? Today we are talking about dynamic time warps,
Of course.
and this
Hence the
is
song.
yes, and I think it's maybe my favorite algorithm name of one that I've encountered so far. Let's do the time warp again. So this is actually kind of a re-record of an episode that, gosh, when did we talk about this
We
last?
recorded that I can just say a very, very long
I
time. It was
remember
one of
us
the,
doing it in the Udacity offices.
yeah, it was one of the very early episodes that we recorded. And this one just somehow never got released for some reason.
Nope. This is the long lost. What's the word I'm looking for?
I don't know. Cousin?
No, it's not a prequel. Sequel. That's
The
the word I'm
long
looking
lost
for.
sequel to the Detector.
Yeah, which, in case you hadn't figured this, okay, so we should step back for just a second.
Yeah,
If you were,
what was that about? The Detector.
if you were one of our more recent subscribers, so in the early days, I
Which
had,
you can go back and you can listen to if you want to.
oh yeah, for sure. I had this vocal affectation. We both do, where when I need to fill a gap while I'm thinking, I tend to say and a lot of the time these ums will be sort of edited out because they don't add anything,
It's
and
part
a
of
lot of
the
time,
podcast editing process.
yeah. But I was noticing as I was editing that when you're editing the vocal files, there's the like sort of a picture that rolls in front of you, and it's the picture
Yeah.
of the sound wave. If that
Yeah,
makes
it's called a
sense.
waveform, and it's a visual representation of the amplitude of the sound. So if I were to clap right now, that would be represented as a sharp spike. And if I say then that's just kind of a little spike with some silence at the beginning and silence at the end.
Yeah, so I was noticing that when I say yeah, I saw one right now. I'm watching myself record. When I say it has a very distinctive shape to it. It looks kind of like it always looked to me a little bit like a tornado that's flipped on its side, or it has a sharp
Oh
edge and
yeah.
then it kind of tapers down. And the sharp edge can go up very quickly, or sometimes it has a little bit more of a slope to it. It can have different lengths, obviously. I can say and that's very short, or I can say and that's a much longer thing.
And this matters because when you were recording, when you were editing, you were looking for the ums to remove them, and you noticed that you could actually see them and almost predict where they were.
Yeah, and so my thought was, well, let's just make a machine learning algorithm that could remove all the ums, and wouldn't that be fun?
And I think your
That's
excuse
just last
was
words, yeah.
because we say a lot, but I don't think you really need an excuse to take on a project like that. Like we're both geeks.
Yeah. Well, totally. Yeah. I mean, let's be honest. Editing out the ums is way easier than actually building an
Yeah.
algorithm that will automatically edit them out for you.
The benefit of us saying a lot is that means that you have enough ums to make a training set to train some algorithm to, take out the ums in the podcast.
Yeah, and so my heuristic in thinking that this would be a good problem, well, good, interesting problem for machine learning, is that if there's a pattern there that I can detect with my eye, basically, that a computer should be able to figure that out if I find the right representation for the data and the right algorithm and so on. I'll be honest, it's really not about the algorithm on this one. I think it's much more about figuring out how to represent the data in a way that goes in and that is amenable to the types of algorithms that we have in machine learning. And this is sort of a time series problem. It also very quickly gets into the realm of signal processing. And the dynamic time warp is actually a signal processing algorithm that I came across in the course of trying to solve one of the problems with the detector. And I thought the dynamic time warp was a super cool name and a super cool algorithm. And so that is where we are today.
Now, I actually wanted to just take a quick step back and talk briefly about how this data is represented. Like, how is the sound of my voice represented? And here we're talking about uncompressed signals. We're not talking about MP3s or compressed audio files, because those are represented a little bit differently. But fundamentally, with an audio file, you have a sample rate. And that sample rate is the number of audio frames, or the number of times per second that it records some voltage or some number that corresponds to the position of the diaphragm of the microphone. So as I'm talking into the microphone, this little thing called the diaphragm, this little thin, flimsy thing, is moving back and forth and creating a voltage, which is being recorded by the microphone and sent into the computer, and then recorded 44,100 times per second, at least with the way that we're recording. And you can tell the computer to record more quickly, and you get a higher quality audio file out of that, like if you're recording a song, for example. So fundamentally, what this means is for every second of audio, you have 44,100 different data points.
Yes, but that is not a format that goes into sort of out-of-the-box supervised learning algorithms very nicely. What you want for a supervised learning type setup is something that you can stick into a matrix. There are some, maybe details around the edges of this, but basically if you can put it into a matrix, you can stick it into a supervised classification problem. However, matrices have kind of a standard shape to them. One of the things about a matrix is that one row in a matrix can't have 100 columns, while a different row in the same matrix has 1,000 columns. And yet there isn't a well-defined number of samples that I want to have that I can call an because some ums might last 1 second, and some ums might last a half second, and some of them might last 3 seconds. And so I have all these different lengths of audio sampling, and they all have sort of the same shape, but the shape can be a little bit different from one to the next, and they can also be stretched and squeezed, and lining them up on top of each other is actually a pretty challenging problem.
Right, especially because you don't just have a bunch of chunks of audio necessarily, and you're just checking to see if they're ums. You've got this huge, gargantuan audio file, and you need to figure out both the right way to slice it up to compare things, and also how much to stretch it or squeeze it.
Right. And so that sort of parsing, figuring out where the windows need to be to collect samples, like examples of what an looks like, that's something that we'll skip for the time being. But the issue of the stretching and the squeezing and getting everything to a standard length, that's where the dynamic time warp comes in. And so the problem of a dynamic time warp is basically you have two different time series objects. So it would be, let's say, this thing that I'm about to say, and then the second thing that I'm about to say, and I have these two different things. It's ostensibly the same word that I'm saying. They have very different temporal lengths, and they might have slightly different tone in them, so that, say, the falling edge of the first might be steeper than the falling edge of the second one, or there might be some undertones in one of them, things that maybe you couldn't even hear, but that would make it so that if you were to just naively stick one on top of the other, it would say, oh, it doesn't look like these time sequences map up that well, so therefore we don't think that these are really the same thing, when in fact they are the same thing. And so you have to figure out how to probably stretch the short one or squeeze the long one, and also maybe move around some of the substructure a little bit, stretching and squeezing even within the sound of the in order to get things to line up properly.
That's a really, really tricky problem.
Yeah. So, and that's what the dynamic time warp does, is it's basically an algorithm. The way that you can think about it visually a little bit is, imagine that you have, let's say for the sake of argument, that the first that I said there was 1 second long, and so it was 44,100 time slices. And then let's say that the second one is 2 seconds long, and so it's 88,200. So what you do is you make a rectangle, and it's 44,100 along one axis, and it's 88,200 along the other axis. So you sort of like have one of your time series is the rows, and then the other one is the columns. And then what you need to do is you need to come up with something that's sort of a compromise in between the two that gives you a mapping from a point in A into its sort of analogous point in B. So you kind of have to find a path sort of along the diagonal of this rectangle that you've just made. So if there's no particularly weird substructure, if they have literally the same number of, or I should say the same pattern of samples in them, but one of them just takes twice as long, then what it's going to look like is that for every step that you make in the short you take 2 steps in the long and then you just kind of like move along 1 step of A, 2 steps of B, 1 step of A, 2 steps of B, and sort of things line up kind of nicely along like the diagonal that traces out in the rectangle that you've made.
Right. That makes sense.
Yeah. And so, but then you can imagine that it's not always the case that there's this easy mapping that you can find, and that there might be some of that internal stretching and squeezing that we were talking about. And so then what ends up happening is that you wander off of the diagonal. So you might have to do something like you take 1 step of A, but you might have to take 3 or 4 steps of B to sort of end up in the same place. And so then you would wander a couple more squares off of the diagonal as you're not moving forward in A, but you are moving forward several steps in B. And so you can imagine that there's a number of different versions of sort of the path that you can trace along that are similar to the diagonals, but not exactly along the diagonals.
Yeah, maybe a little more squiggly or something like that.
Exactly. And so the dynamic time warp is basically a way of looking at all the different squiggly paths that you can trace out and finding one that sort of maximizes the joint likelihood across the 2 different time series at the same time. So it's kind of solving the problem of what's the best compromise that we can find of all the compromises that are available to us, so that we end up starting at the same place and ending at the same place, and then everybody's been stretched and squeezed so that we can come up with some sort of agreement about what happens in the middle.
So Katie, what would it sound like if we ran your detector on this episode? So apparently we haven't.
Oh, no, yeah. Guess who's got 2 thumbs and isn't really working on this anymore? This gal. Yeah, no, it's interesting. Yeah, it was interesting to get all the audio reading in and to get some of this dynamic time warp software up and running, and then I just kind of don't care that much. It's so much easier to just not say that much than it is to go nuts with this algorithm. I mean, it's fun and it's interesting and things like that, but there are other things that I am more excited about. So it's pretty backburnered at this point. I haven't worked on it in a long time, but I always hated it when I was a kid and I would watch TV shows and there would be some kind of interesting thing that got started at the end of like a TV season, like a
cliffhanger thing?
Yeah, and then it just starts up the next season and it never acknowledges that there might be this
so that's what this episode is.
Yeah, is it's me kind of working through my cathartic moment of acknowledging that I'm never going to finish the side project. But it's really interesting. So it's worth talking about.
Hey, and we got 2 episodes out of it, so that's a win. Linear Digressions is a Creative Commons endeavor, which means you can share or use it any way you like. Just tell them we said hi. To find out more about this or any other episode of Linear Digressions, go to lineardigressions.com. And if you like this podcast, go ahead and leave us a review on iTunes so other people get to listen to this content too. You can always get in touch with either of us. Our emails are ben@lineardigressions.com and katie@lineardigressions.com in case you have comments or suggestions for future shows. You can tweet us at lindigressions. Thank you for joining us, and we'll see you next time.